This is question 4 from the SACE Stage 2 Physics Course Companion from section 2.1 Electric Fields. This is a bit of a challenging question. Here we have three charges, Q1, Q2 and Q3, all in a line, and the net force acting on Q1 is 0. We need to determine the charge of Q3. So the best way to think about this is just draw a bit of a picture to see what's going on. So if we have Q1 in the middle, then the force due to Q2, let's say it's attractive force going this way. So we have F12 like that, and therefore the force due to Q3 will be going in the other direction, and we know that the net force is 0. Therefore, since the net force is 0, the force due to Q2 has to be equal to the force due to Q1. So now we can just use Coulomb's law here. So 1 on 4 pi epsilon naught Q1 Q2 on the distance squared, so 0.7 squared centimeters, has to be equal to 1 on 4 pi epsilon naught Q1 Q3 on 0.35 centimeters squared. So here we get a lot of cancelling out occurring. So the 1 on 4 pi epsilon naughts cancel out, the Q1s cancel out, so essentially we have Q2 on 0.7 centimeters squared equals Q3 on 0.35 centimeters squared. Therefore, we can write an expression for Q3 pretty easily. So Q3 will be equal to 0.35 times 10 to the minus 2 squared on 0.7 times 10 to the minus 2 squared multiplied by Q2. Now here, since we have the same units at the top and bottom of this fraction, we can just cancel those out. We know that 0.35 is half of 0.7, so this is actually just as simple as writing 1/2 squared multiplied by Q2, so a quarter Q2, which is easy enough now. Since Q2 is 4 microcoulombs, it'll just be a quarter of 4 microcoulombs, which is 1 microcoulomb, and that's fairly easy. Now, interestingly, we can think about what the charge of Q3 might be. So here, the situation is going to be kind of symmetrical, so expect that Q3 is going to be a positive charge, but it's good just to think it through anyway. So we have what's on the far left, we have Q2 as positive, and if Q1 was, say, negative, that would mean that the force between the two would be attractive, so the force on Q1 would be directed this way, meaning that the other force would have to be directed in the other direction. The only way for that to be possible is to have a positive charge over there. Similarly, if we have positive charge for Q2 and suppose that Q1 was positive, then the force acting on Q1 due to Q2 would be repulsive, so it'd be this way. So our charge would have to be creating a force which is opposite to that, and the only way for that to be possible is if it's a positive charge. So it really doesn't matter what the charge of Q1 is. Here, Q3 must be positive regardless, and that's just an interesting conceptual process to work through, just to make sure that what we expect is the correct answer is the correct answer. And that's about it. Now, it's a fairly challenging question. The hardest part's probably getting started, but after that the rearrangement and substitution is fairly straightforward. And that's it.